The next topic of great importance that merits our attention is the balancing of redox equations by the so-called half-reaction method or ion-electron method. We do this by first balancing the equation chemically. What does that mean? It means we must make sure that we have the same number of atoms of each element on the left and on the right. We do this by adding hydrogen ions when we work in an acid medium, or hydroxide ions if we work in an alkaline medium, as well as water molecules, etc. We balance electrically by adding electrons to the right-hand side of the oxidation half reaction or to the left of the reduction half reaction, because chemical equations that involve ions must always be balanced both chemically as well as electrically. We now add hydrochloric acid to iron sulfide in this flask. Then hydrogen sulfide gas is developed, and as you can see, the yellow color of the iron 3 chloride in this test tube is turned light green, and you also get a milky suspension of sulfur formed. Let's just wait for a sec for the reaction. Can you see it's turning green now? And can you see the milkiness of the sulfur formed? So sulfur is one of our products. This here is the essential equation of this reaction, where iron 3 ions has been reduced by hydrogen sulfide to iron 2 ions, and sulfur is also formed. The first step is always to write the oxidation half reaction. In this case, we see the reducing agent undergoes oxidation to sulfur, because you see hydrogen sulfide and sulfur obviously must be connected, because the sulfur here can only come from hydrogen sulfide. To balance chemically, we see that there are 2 hydrogen atoms on the left. So the hydrogen sulfide, because it is a weak acid, will dissociate to form hydrogen ions. And now we have 1 sulfur on the left, 1 sulfur on the right, 2 hydrogens on the left, 2 hydrogens on the right. So this equation is now balanced chemically, but not electrically, because on the left, the equation is neutral. And here we have 2 positive charges, so we need to add 2 electrons to the right-hand side, like we always do for oxidation half reaction, to balance the equation also electrically. The next step is to write down the reduction half reaction. We see that iron 3 must be connected to iron 2, obviously, and chemically this half reaction is already balanced, because we have 1 atom of each on each side of the equation. And by adding 1 electron to the left, we can also balance it electrically, because we have now 1 negative charge and 3 positives, a total of 2 plus. And on the right, we have 2 plus. The next step is always to multiply these half reactions by suitable numbers to make the total electrons given off in the oxidation half reaction equal to the number of electrons taken up by the reduction half reaction. And then the 4th step is to add the 2 balanced half reactions. Okay, the reduction half reaction is multiplied by 2 in this case. That will give us 2 iron 3 ions and 2 electrons and 2 iron 2 ions, because we multiply every term throughout the equation. Okay, now we see that 2 electrons has been delivered at the oxidation half reaction, and 2 electrons was taken up by the reduction half reaction. So if we add the 2 balanced half reactions, we get the cell reaction. The next step is to delete the electrons, which will be on both sides, and any ions or molecules that may occur on both sides of the equation. And then we have the cell reaction, or the balanced equation, as follows. If this reaction was carried out with iron 3 chloride, it means that chloride ions will be the spectator ions, and the final formula equation will be as follows. The balanced half reactions that we developed for the balancing of this last equation can often be found directly from the standard reduction potential series, where we always find the oxidation half reaction higher up in the series. And as you can see, we must always reverse the oxidation half reaction if we use it for balancing. And we find the reduction half reaction lower down in the series. Let us see what happens if we bubble hydrogen sulfide gas through a solution of potassium dichromate. In this test tube, I have potassium dichromate solution, which I acidified with hydrochloric acid. I'm now going to add hydrochloric acid to the iron sulfide in the flask to develop hydrogen sulfide gas. And then you'll see the color changes to green because of the formation of chrome 3 ions. which are green, olive green. And you also have a cloudy suspension of sulfur formed. Can you see the green appearing now and the orange disappearing? And there's the sulfur also forming now. Over here, we have the essential equation of the reaction, where the dichromate ions have been reduced by hydrogen sulfide to form chrome 3 ions, and the hydrogen sulfide has been oxidized to sulfur. The first step is to write the oxidation of reaction, and like we had for the example before this one, we find that hydrogen sulfide will dissociate to 2 hydrogen ions, so this is balanced chemically, and if we add 2 electrons to the right-hand side, we also balance the equation electrically. The next step is to write the reduction of reaction of the equation, where dichromate ions undergo reduction to chrome 3 ions. We balance chemically first always. We see we have 2 chrome atoms over here, so we have to put a 2 in front of chrome 3 to balance the chrome atoms. We find there are 7 oxygen atoms in dichromate, and the oxygen atoms always turn into water in the case of redox reactions. So we have to add 7 water molecules to the right to get 7 oxygen atoms. But this leaves us with 14 hydrogen atoms, which is derived from hydrogen ions, which we have to add to the left, which we get from the acid. As far as the chemical balancing is concerned, this reaction is now okay, because we have equal numbers of atoms of each element on each side of the equation. But let us see what we have to do to balance the equation electrically. Here we have 1 particle with 2 negative charges, so we have 2 negative charges in all. And here we have 14 positive particles, or protons, each with a positive charge, giving 14 positive charges. Subtracting the 2 negative charges, we have a total positive charge on the left of 12 plus. On the right, we have 2 particles, each with a charge of 3 plus, so it gives a total charge of 6 plus. So we have to add 6 electrons to the left to balance electrically, to get 6 positive charges on each side of the equation. If we now look at the electrons in the oxidation of reaction, we see the LCM of 6 and 2 is 6. So we have to multiply the oxidation of reaction by 3 throughout. You can see here the oxidation of reaction, when multiplied by 3, will give us this equation, where 6 electrons are released, which will be the same as the number of electrons accepted in the reduction of reaction. When we add the 2 balanced half reactions, we get this balanced cell equation, but we still have to delete electrons. You can see there are 6 electrons on the right, so we delete the electrons on the left and right. We see we have 6 protons on the right, so if we take away the 6 protons, we also remove 6 protons on the left, leaving us with 8 protons. If we add the 2 half reactions, we get the cell reaction, which is now balanced chemically as well as electrically. The formula equation of this reaction, if we use HCl to acidify, is as follows. And if we use sulfuric acid to acidify, we get this balanced equation, where we now use 4 molecules of sulfuric acid, which will give us 8 protons as required. We could also obtain the balanced half reactions directly from the standard reduction potential series, where once again the oxidation of reaction is found higher up in the series and must be reversed when used to balance equations. And the reduction of reaction is found lower in our series over here. Now we want to see what happens in our next example if we bubble sulfur dioxide gas through a solution of potassium permanganate. In this test tube I have a solution of potassium permanganate, the purple color being due to the permanganate ions. And over in this flask I have some sodium sulfite. And when I add hydrochloric acid to it, I get sulfur dioxide as one of the products. Let's just add the acid and see what happens if I bubble it through. Can you see the solution turns colorless due to the formation of colorless manganese ions? Now, over here we have the essential equation of this reaction, where permanganate ions are reduced by sulfur dioxide to form manganese ions, and sulfate ions are also formed. The first step is always to write the oxidation of reaction. Now, the sulfur dioxide is the reducing agent, so it must undergo oxidation. So it is oxidized to sulfate ions. We see there are two more oxygen atoms on the right. So the oxygen atoms are obtained from water, so we have to add 2 water molecules to the left. We now have 4 hydrogen atoms here, and therefore we have to add 4 protons or hydrogen ions to the right, because the hydrogen in the water is always turned to hydrogen ions. Now this half reaction is balanced chemically because we have 1 sulfur atom here, 1 over here. We have 2 oxygen atoms plus another 2 is 4, and we have 4 oxygen atoms over here. We have 2 times 2 is 4 hydrogen atoms, and we have 4 hydrogen atoms on the right. The next step is to balance the equation electrically. On the left we have neutrality, and on the right hand side we have 1 sulfate ion with 2 negative charges, and we have 4 protons or hydrogen ions, each with a positive charge. So the total charge on the right will be 2 plus, which means we have to add 2 electrons to the right to make this side also neutral. Our next step is to write down the reduction half reaction as usual. The reduction half reaction is as follows. The permanganate ions are reduced to manganese ions. The 4 oxygen atoms in the permanganate ion are converted to 4 water molecules, because you see we'll have 4 oxygen atoms in the water. But now we have 8 hydrogen atoms, which means we have to add 8 hydrogen ions or protons to the left, because that's the acid that we add, because we work in an acid medium. And now this half reaction is balanced chemically because we have 1 manganese atom on the left and 1 on the right. We have 4 oxygen atoms on the left, and we have 4 on the right. We have 8 hydrogen atoms, and we have 2 times 4 is 8 hydrogen on the right. But this half reaction must still be balanced electrically. So we look on the left and we see we have 1 permanganate ion with a negative charge and 8 protons, each with a positive charge. So we have 7 positive charges altogether on the left. But we have 1 particle with 2 positive charges on the right, which means a total of 2 positive on the right. And now we have to add 5 electrons to the left to make the charge the same on both sides. The LCM of 5 and of 2 is 10, which means I have to multiply this oxidation half reaction here by 5, the oxidation half reaction, to get this equation where we have 5 sulfur dioxide molecules reacting with 10 water molecules to produce 5 sulfate ions and 20 hydrogen ions and 10 electrons. We have to multiply the reduction half reaction by 2 to give us 2 permanganate ions and 16 hydrogen ions and 10 electrons, converted to 2 manganese ions and 8 water molecules. The next step is to omit the electrons. We delete electrons from both sides. There are 10 on this side and 10 on this side. And then I find that I have 8 water molecules on the right-hand side here. If I take 8 water molecules away from the left, it leaves us with 2 water molecules. We have 16 protons on the left, but we have 20 on the right, which means if I remove 16 protons here, we are left with 4 protons. Adding these 2 half reactions, we obtain the cell reaction where 2 permanganate ions react with 5 sulfur dioxide molecules and 2 water molecules to produce 2 manganese ions, 5 sulfate ions, and 4 hydrogen ions. And this equation is now balanced both chemically and electrically. Let us check. We have 2 manganese ions on the left and 2 manganese on the right. We have 2 times 4 is 8 oxygen, plus 2 times 5 is 10, it's 18, plus another 2 is 20 oxygens on the left. And we have here 5 times 4 is 20 oxygens on the right. We have here 5 sulfur atoms on the left and 5 sulfur atoms on the right. We have 2 times 2 is 4 hydrogens on the left and 4 hydrogens on the right. So it balances chemically. And finally, we check whether this equation balances electrically. On the left, we have 2 permanganate ions, each with a negative charge, so the total electric charge on the left will be 2 negative. On the right, we have 2 manganese ions, each with 2 positive charges, which means we have 4 positive charges. We have 4 protons, each with a positive charge, so we have a total of 8 positive charges. But we have 5 times 2 is 10 negative charges on the sulfate ions, so the total charge on the right will also be 2 negative, and this equation now balances both chemically and electrically. Now, if we add the spectator ions, potassium ions, we get this final formula equation for the reaction, which is also balanced. The half reactions that we used for balancing this equation could also be read off straight from the standard reduction potential series as we did before, where the oxidation half reaction is always found higher up in the series, and as we said before, it must be reversed when you balance equations, and the reduction half reaction is found lower down in this case.
Thus far, we have only considered electrochemical or galvanic cells where chemical potential energy is converted into electric energy. The opposite process is also possible. In electrolytic cells, electric energy is converted into chemical potential energy. This happens by the process called electrolysis of a conducting ionic solution called an electrolyte.
Refer to page 11.3 of your Module 5 workbook, and also refer to the DVD for a complete explanation and demonstration of the electrolysis of a solution of copper 2 chloride.
Perhaps the most important application of the electrolytic cells is the chlor-alkali industry. We look at the so-called membrane cell. Electrolysis of the electrolyte, sodium chloride or brine, is used to produce millions of tons of chlorine gas, sodium hydroxide, also called caustic soda, and some hydrogen gas annually.
To help you understand the stoichiometry of the overall balanced equation of the process, we shall consider the reaction of every 2 formula units of sodium chloride and the 2 water molecules. The 2 formula units of NaCl entering the anode cell here at the bottom dissociate as follows in water to form 2 positive sodium cations and 2 negative chloride anions.
The 2 chloride anions are attracted to the positively charged anode where they undergo oxidation to form chlorine gas, when they lose 2 electrons to the anode. Let's look at the oxidation half reaction. A plastic polymer membrane separates the 2 half cells. This is a so-called positive ion permeable membrane which only allows the positive sodium cations to pass through to the negative cathode, attracting them.
At the cathode, water is preferentially reduced to hydrogen gas H2 and 2 hydroxide anions, since water is a stronger oxidizing agent than sodium cations. Let us look at the reduction half reaction. When we add the 2 half cell reactions, we obtain the overall cell reaction in ionic form.
When the 2 sodium cations arrive at the cathode, they combine with the 2 hydroxide ions to produce 2 formula units of sodium hydroxide. The overall formula equation is sodium chloride reacts with water to give chlorine gas, hydrogen gas, and sodium hydroxide.